Let me introduce you to the mole. Not that mole. No, please.
I found this on the web. Moles are growths on the skin. They happen when pigment cells in the skin, called melanocytes, grow in clusters. This is from medlineplus.governor.
Let me introduce you to the mole of science, chemistry's own unit of counting. Because who needs dozens or baker's dozens when you can have Avogadro's number, right? Moles enable us to measure atoms in bulk without needing an electron microscope. Obviously because they are very, very tiny. Since it is practically impossible to weigh out one atom or molecule because obviously they are very small and then react it with another one, chemists use these counting units which are more practical. Examples of counting units are banks, which weigh out the mass of certain denominations of coins instead of actually individually counting the number of coins one by one. In chemistry, we count atoms and molecules by weighing them, and the standard of counting is the mole, which represents the amount of particles, be they atoms, molecules, compounds, ions, you name them, in any substance. Alright, so take note that a mole counts the number of particles in a substance. And the mole is represented by the constant L, the Avogadro constant L, named after the discoverer, gentleman Avogadro. And the Avogadro constant is a number which always remains the same, and it states that 1 mole of any substance is always equal to 6.023 times 10 to the power 23 number of particles. So you can find in some text it will say 6.02 times 10 to the power 23. In some text it will say 6.023 times 10 to the power 23. This number is in standard form. Standard form is a notation which enables us to be able to use numbers, to be able to count, to compare. Because this number would have 23 zeros, 1 and 23 zeros, it would be a very big number. So it is shortened to standard form. For a video on standard form, you can check out the link in the description as well as the link displayed on the corner of the page. Now, calculations involving the mole use this concept. To find the number of moles, you are going to divide the given mass of the substance over the molar mass. We're going to look at now some of the calculations which involve this empirical formula, which involve the usage of the mole. One of the most important calculations involving the mole include the usage or the calculations of empirical formula. The empirical formula is the simplest one-number ratio or formula of the reacting elements in a compound. For example, if our compound is water, we have 2 hydrogens and 1 oxygen, which means that this is the simplest ratio. Another compound may be, for example, hydrogen chloride, which is our hydrochloric acid. This one is in its simplest number ratio because there's 1 hydrogen and 1 chlorine. Alright? Maybe it is different, obviously, of course, from the formula of the actual number of molecules in a substance, because let's say, for example, 1 cup of water will not only have 1 molecule or 1 compound of water, it would have maybe thousands, millions, or perhaps billions. And to find the actual number, we would have to experimentally maybe weigh the mass of the water, subtract the mass of the container, and then divide by the moles which we have calculated. For us then to understand the empirical formula, we need to appreciate how to find the relative atomic mass, which we call AR of an atom, and the relative molecular mass, which we call MR of a compound, and also how to calculate the number of moles. So to find the relative atomic mass of a substance, you can find it by, let's say, for example, we have our atoms here, elements, hydrogen. These are 3 isotopes of hydrogen. These are isotopes. Alright, so for these isotopes, you can see that these numbers are the ones which are different. So it means that the number of the nucleons are the ones which are different. This one only has 1 proton. This one has 1 proton and 1 neutron. And this one has 1 proton and 2 neutrons. This is the relative atomic mass. The atomic number here is giving us the relative atomic mass of the substance, because they are being compared by carbon, where the carbon 12 atom is a mass of exactly 12 units. So this is why it's called the relative atomic mass, because all of these masses are measured relative to carbon. This carbon has got 12, which means it has got 6 protons and 6 neutrons. So this 12 is giving the relative atomic mass of the carbon. Where relative molecular mass is involved, this is the sum of the relative atomic masses of all the atoms present in a molecule. For example, in water, we saw that it is the common hydrogen which we use has got a relative atomic mass of 1, so it will be 1 plus 1, and then oxygen has a relative atomic mass of 16 if you check from the periodic table. So it will be 1 plus 1 plus 16, giving you 18, right? Another compound which we can use is hydrogen chloride, which has got 1 plus chlorine 35.5 or chlorine 37. These are two isotopes of chlorine. If it is chlorine 35.5, then the relative molecular mass with the 35.5 plus 1, which is 36.5, which you can see here, or it will be 38 if it is chlorine 37. And the relative formula mass is the sum of all the relative atomic masses of the atoms present in a formula unit of a substance, which is basically the same as relative molecular mass, except that it's mainly used for giant ionic or giant covalent or giant ionic structures, but it's basically the same as relative molecular mass. Now let's move on to calculations involving the mole. To find the number of moles, we said we simply calculate the mass divided by the molar mass. For example, number of moles in, let's say, 20 grams of a compound like water, which is simple. What we simply do is number of moles N is equals to the mass, 20 grams, over the molar mass, which is 2 plus 16, which gives us 18. Then we use our calculate to calculate this one, 20 over 18, and this gives us 1.111111. So we have 1.11 moles. Very simple, right? Here we've been given a problem. We need to calculate the empirical formula, which we said is the simplest ratio formula. Question says, in experiments to make magnesium oxide, a constant ratio was formed between the reacting amounts of magnesium and oxygen. If 0.24 grams of magnesium was burnt, then 0.40 grams of magnesium oxide was formed. Since the keyword there is constant ratio, it means that the amount remained the same. So by simple logic, we can deduce that if mass of product was 0.40 grams and mass of magnesium was, then it must mean that the mass of oxygen which reacted must be a difference between these two. Since it's a constant ratio, 0.40 minus 0.24 would give us 0.16. So it is evident here that already the mass of magnesium which combined were given 0.24, and obviously the mass of oxygen is 0.16. So now we need to find the molar mass, and this can only be done using the periodic table. On the periodic table, the mass of magnesium can be found this side, and it is 24, and the mass of oxygen is found this side, it is 16 grams per mole. All right, now let's use the information which we have so far. We've deduced that since 0.24 grams of magnesium was combined to form the product, then it must mean that 0.16 grams of oxygen was used. And we've also used the molar mass from the periodic table. Now we need to calculate the number of moles. Number of moles N. N equals to M over MR, which is mass, which we have here, 0.24 divided by 24. So since this is grams, this is grams per mole, we are going to use a calculator. 0.24 divided by 24 gives us 0.01 moles. These are now moles. And again here 0.16 divided by 16. This is grams per mole. It's going to give us 0.01 moles. You can already see that these are 0.01 and 0.01. So we divide by the smallest number from both sides here, which is 0.01, since they're the same. We divide by 0.01, and here we're going to get 1:1. So you can see if we divide 0.01 by 0.01, obviously we're going to get 1. You can see here that 1 mole of magnesium reacted with 1 mole of oxygen. So the simplest ratio of reaction between magnesium and oxygen would be MgO. This is our formula for magnesium oxide. Let's try out another one. A sample of silicon 4 oxide or silica is found to contain by percentage 47% by mass of silicon. Calculate the empirical formula. Again, you can see here that we've been given percentage instead of mass now. So this side we have 47%, and then this side we have 100 minus 47, which gives us 53. So this side will be 53% when this side is 47%. Now, in a 100 gram sample, since we've not been given a specific mass, we're going to use this assumption that since the mass is constant, then it must mean that we can give a certain or a particular or arbitrary mass, which we can use as a reference. For example, we can use 1 kilogram, but it would be too much. We'll still need to come back to reduce it to its lowest terms. So we can use in a small sample of 100 grams. So in a 100 gram sample, 47% of 100 grams, 47% of 100 grams. This would give us 47 grams. And again, in a 100 gram sample, this one would give us 53 over 100 times 100, and this would give us again 53 grams. Now we have mass. Now we need to look to find the number of moles, which you said the number of moles is found by calculating the given mass over MR. Now we have deduced the mass by using the different percentages, and it is 47 over the MR. We will need again to look at the relative atomic mass of silicon, and for oxygen we already saw it in the previous one. It is 16. So here it's 53 over 16, and here we will deduce it. Let's look again at the periodic table. On our periodic table, our silicon is here, and its relative atomic mass is 28, and our oxygen is here. Its relative atomic mass is 16. All right, so let's try now to deduce. So we've already calculated that one, and the mass in a 100 gram sample, we've already deduced that one. This one is 47 grams, and here it's 53 grams. The number of moles, N equals to M over MR, which is equals to 47 grams over, we found this one to be 28, and we're going to calculate using a calculator. 47 should give us 1.68. We round it to one decimal place, two decimal places. To give us 8 moles, and we do the other one, 53 And we do the other one, 53 divided by 16. This will give us 3.3125. Now, for us to find the simplest ratio, we look at these two figures. These are moles. So what we simply do is we divide by the smallest one so that we can find the simplest whole number ratio. So since here this side is 1.68 and this side is 3.3128, we can simply divide both sides by 1.68. So we're going to say 1.68 over 1.68, here 3.3125 over 1.68. This will give us 1.97. This gives us 1, and this gives us 1.97, which we can round off to 2. So the simplest molar ratio, or the simplest combination ratio of silicon dioxide is 1 silicon bonding with 2 oxygen, SiO2, silicon dioxide. All right.
Silica is a major component of quartz, glass, sand, and cement.
Let's try another example. Phosphorus burns in air to produce white clouds of phosphorus oxide. From experiments, it is found that the oxide also contains 44% phosphorus. Calculate the empirical formula. What we will do is we are going to do the same which we did. We've been given that we have, by percentage of mass, 44% phosphorus. So it means that to find the mass of oxygen by percentage, it will be 100 minus 44, giving us 56% by mass. In a 100-gram sample, it will be 44 over 100 times 100 grams. This is 44%, and this will give us 44 grams. And in a 100-gram sample, this is 56% of 100, which will give us 56 grams. Now we need to find the number of moles for phosphorus and the number of moles for oxygen of phosphorus. So phosphorus is here. It is a relative atomic mass of 30, and again our oxygen is here with its 16. So we've already deduced the masses from the periodic table. Here we can see that it is 30.1 and oxygen is simply 16. We've already deduced that phosphorus has 44%, and therefore it must mean that oxygen has 56%. The mass in a 100-gram sample is 44% of 100, giving us 44 grams. And here, the mass in a 100-gram sample is 55% of 100, giving us 56% of 100, giving us 56 grams. Then the number of moles, which we say we calculate by finding the mass over the MR. This is our deduced mass, 44 divided by the MR, which is 31 grams per mole, which we found from. And then here it is 56 over 16, which we found from our periodic table. What we are going to do now. This gives us 1.4. This gives us 3.5. Here, we're going to find the simplest ratio. We're going to divide 1.4, divided by the smallest one from both sides, which is 1.4. 1.4 divided by 1.4, giving us 1. 3.5 divided by 1.4, we're going to use a calculator. This gives us 2.5. Now to find, since you can see that one side has got decimals and it's 2.5, so the simplest way to make this one a whole number is to just multiply it by 2. So multiply this side by 2, also multiply this side by 2, and we are going to get the simplest whole number ratio being 2:5. So it means that 2 moles of phosphorus are going to react with 5 moles of oxygen. So this is the simplest whole number ratio. So the formula would come out like this: P2 P2O5. The question continues. However, it is found experimentally that the relative molecular mass of the compound is actually 284. Calculate the actual molecular formula of phosphorus oxide. So that molecular formula which we calculated is simply simple ratio of the combining elements. That does not give us the right to say that that is the actual molecular formula. The actual molecular formula of a compound can only be found experimentally, whereas in this instance when we have extended information or some extra data. All right. So here we've been given that the actual relative molecular mass is 284 instead of. So to calculate this, we find the sum of the relative atomic masses in the empirical formula. So it will be for phosphorus, 2 times phosphorus and 5 oxygen. So phosphorus, we've already looked at it, it is 31. So we multiply 2 times 31, giving us 62. And then oxygen is 16. So 16 times 5 gives us 80. So 80 plus 62 gives us 142. But you can observe that the relative molecular mass is twice, because if we multiply this number by 2, 142, it gives us exactly 284. So you can see here that the actual relative molecular mass is twice this value, and hence the molecular formula, the actual molecular formula of phosphorus oxide is P2O5 times 2, or to make it more simple, P4O10. What this means is we have 2 molecules of phosphorus oxide, or P2O5, coming together to form 4 phosphorus and 10 oxygens in one. The actual molecular formula of phosphorus oxide will be P4O10. You may take note that in this case, the phosphorus oxide that has been produced, which we found by saying P2O5, is just the empirical formula. And we can only find the actual molecular formula using experiments. We cannot deduce the actual molecular formula without having an experiment done. Or like we are saying that the empirical formula only shows us the simplest whole number ratio of the compound, but not the actual molecular formula, which we said can only be found by experiment. Now let's look at how to calculate the relative molecular mass and the relative molecular formula of a hydrate salt.
I found this on the web. Hydrated salts are salt compounds that have water molecules attached to the salt molecules. This answer is from differencebetween.com.
Thank you, Siri. Noted. The mass of water present in crystals of hydrated salts is always a fixed proportion of the total mass, and the formula of the salt can be worked out by a method which is similar to that one which we used to calculate the empirical formula of the compound. Let's try a question. If 5.0 grams of hydrated copper 2 sulfate crystals are heated to drive off the water of crystallization, the remaining solid has a mass of 3.2 grams. Calculate the formula of the crystals. Here we can observe that since the mass of the hydrated copper sulfate crystals is 5.0 and the remaining solid has a mass of 3.2, it means that the mass of the water which evaporated is 1.8 grams. Alright, so a simple calculation, 5.0 minus 3.2. We are going to look at how we can find it. We said the formula is almost the same, or the way is almost the same as we use for finding the empirical formula of simple compounds. So for us to calculate the molar mass, we need to find the relative atomic masses of all the elements here in this compound, and also the relative atomic masses of all the elements here in this compound. So it will be, let's look at the periodic table. The relative atomic mass of copper here is rounded off is 64. So we have 64 from copper plus the relative mass of sulfur is 32, and the relative atomic mass, copper sulfate has got 4 oxygen plus 4 times 16. This is going to give us 160. We use a calculator. This gives us 160. Therefore, here in our table, we are going to write up the molar mass is 160 grams per mole. And here it is, we've already calculated this one in a previous example. This is 18 grams per mole. Then we're going to calculate the number of moles, which we say we found by doing this, m over mr. And here the mass is 3.2 over 160. And here it is 1.8 over 18. All right, this one is very simple. So here this one gives us 0.02 moles, and this one gives us 0.1 moles. Now, since this one is the smallest, we are going to divide both sides by this. So we're going to divide this side 0.02 over 0.02, giving us 1. And we're going to divide this side 0.1 over 0.02. Or we can also simply put it as this. So here we're going to find that we can multiply this by 2 decimal places, since this number, the denominator, has got 2 decimal places. So we multiply both the denominator and numerator by 100. So it will be 1, 0, 10 over 2, giving us 5. So you can see that the simplest combination ratio of this hydrated salt will be copper sulfate 1 times 5 water of hydration. So it will be like this. We put this point here. We put a point here to show that to show the water of hydration. All right. So 1 copper sulfate is being reacted or is being hydrated by 5 molecules of water. So this is the simplest combination ratio between copper sulfate and water in the hydrated salt. Calculation in chemistry. Watch this video.